My name is Lalith. I'm a PhD student in the Mechanical Engineering department, and I've been working on lithium-ion batteries for a while now. Today I'll be presenting some of my research on development of high-energy cathodes in batteries, and I'm being co-advised by Dr. Sayre and Dr. Jung-Hyun here. Imagine if you could buy a Tesla for half of what it costs now, and be able to drive that from here to New York without stopping for charging. Think about it, half the cost and double the performance. Wouldn't that be great? Lithium-ion batteries make up for about 50% of the cost of electric vehicles. Reducing the cost and increasing the energy that is stored in these batteries is one of the key challenges for the future of our transportation. A battery stores and releases energy by the simple flow of lithium ions back and forth. In order to discharge the battery, you need to pump the ions into the anode and store that. The battery is a particular device, and that gives a lot of energy output. And the cathode is the only source of lithium in the battery. So in order to extract more energy from a battery, you need to have a thicker cathode. Conventional cathodes have thicknesses equivalent to the size of a human hair, and that is too low to store large amounts of energy. Thicker electrodes can store 10 times as much energy in them, and that means you need fewer number of electrodes to be put together to achieve a given capacity. And that means reduced assembly cost, reduced weight, and better packing. But the problem is this: when the ions travel from anode to the cathode looks like a traffic jam, and the ions have to then navigate their way in those gaps to reach the host particle. Most of the ions don't even make it beyond a few microns, and eventually the battery capacity goes down. There's a simple solution to this. You might have seen these special lanes for buses across major cities in the world, and these are meant for rapid transit of passengers without the obstruction of traffic. What we do is something similar to this. We form cracks within the electrode structures as a way to create special pathways for fast lithium-ion transport. We do that by using a special combination of unique binders, polymeric binders, at a specific temperature, at a specific viscosity, to give control over the crack growth formation. By controlling the cracks, the electrode performance can be optimized. And the binder is unique because it provides adequate strength to hold the electrode together. At the same time, it provides a mechanism to form these cracks within the electrode. Finally, the electrode that we have been able to create has increased energy density by 50%, and the costs are reduced anywhere between 25 to 50% depending on the material that's being used. And very importantly, this process is scalable, which makes it very attractive for the industry to adopt it. Thank you.